showed in your thesis. It's a long and interesting proof. Since then, of course, Irena has been working on many topics in commutative algebra, besides mixed multiplicities, symbolic powers, associated primes of local cohomology, primary decomposition of ideals, Hilbert-Kunz multiplicities, and many other topics that she pursues. But I must say that the greatest contribution of hers is the unique book that she authored with Greg Hunicke. He is also, I'm happy to note that he is in the audience. It is about integral closure of ideals, rings, and modules. And after this book appeared, it became easy for me to train my students, because I would just tell them that master this book and you are ready to do research. So thanks for putting in it. It must have been great effort on your part and on Craig's part to write such a great book. So we are very, very happy to have you in the seminar today. And now I invite you to present your seminar on primary decomposition and powers of ideals.
Thank you so much, Juga, for this wonderful introduction. And by the way, I still have your notes that you gave me from your proof of the case of two different ideals. So, thank you. Yeah. Yeah, so thank you for organizing these seminars and bringing the world together for interesting commutative algebra. So today I want to talk about my recent work with 4 different people on 4 different projects. And it all has to do with primary decompositions of powers of ideals. And all rings, of course, will be Noetherian, so that primary decompositions do exist. There are algorithms for computing primary decompositions. However, some of them are very slow, and when you're interested in primary decompositions of powers, then algorithmically, you still have to work with one ideal at a time, so interesting things happen. So the foundation of all this work is Brodmann's result, who proves that as you vary the powers, the set of associated primes is still only finite. And not just finite, it's constant for large n. And lots of people have done quite a bit of work on this. What is that final stabilized set of associated primes? McAdam did quite a bit of that, Dan Katz, Ratliff, and so on. But that's not the direction I want to go in today. Today I'm more interested in numbers of associated primes of powers. So in the simplest case, if we take ideal generated by a regular sequence, then the set of associated primes is stable. It never changes, so the numbers don't change, whatever it is. And here is, in part B, this is an example of a prime ideal. And because it's not a complete intersection, the higher powers have an embedded component, and by quasi-homogeneity and heights, that embedded component must be the maximal ideal. So all higher powers have the ideal generated by the variables x, y, z associated to it. So here the number of primes increases. And we'll come back to this particular example later in the talk. And here is another example that we will come to later as well. This is a monomial ideal. There's only one minimal prime generated by x and y, but because of that generator in blue, there is also an embedded prime x, y, z. But then when we take the square or any power of this ideal, that's the same as taking the power of the ideal when we remove that blue generator. So then there are no more embedded, no z appears anymore. So the associated primes of higher powers are just the one minimal prime ideal. Now I want to look at some modifications of this ideal in part C. And the words splitting and spreading come from my work with Kim, Jessie Kim. So we call splitting if we replace one variable with a product of variables. So this is the image of a faithfully flapped map. And then spreading is when you take any one variable. Well, spreading is a little more complicated, but the effect here is that we're replacing the generator x squared y squared z with n generators, x squared y squared z1 through x squared y squared z sub n. Okay. And then we can play with splitting of spreading, and maybe we want to split z1 through zn, so not just one variable, but all of these n variables. And so the numbers of associated primes when we take powers, because these blue generators are not needed in higher powers, then for higher powers we still have just one associated prime, namely the minimal one, but the associated primes of the first power are, well, just of the original ideal. Just for splitting, we get n embedded primes plus one minimal. For spreading, we still have just the one embedded prime, but the difference is that once we have spreading, then the heights of that embedded prime get bigger. So splitting doesn't change the heights of the associated primes, it only changes the number, and spreading doesn't necessarily change the number of prime ideals, but it changes their heights. And so that will be used later. So these ideals B and C will come up later again. And then I want to list a few more examples of set numbers of associated primes of powers of ideals. Some of these are well known. In the D and E, the number of associated primes increases as we increase n. And in the example F by Kaiser, Stelik, and Shkrekovsky, the numbers basically increase, except that there is that one drop. The maximal ideal is associated to I cubed, but not to I to the fourth. And just because the maximal ideal then is no longer associated doesn't mean that the number should go down. Maybe there are other associated primes that come in, but here the number does actually go down. So I want to talk about this property of associated primes that's called persistence. And it is a rather natural property, namely that the set of associated primes of the nth power, all of those primes are also associated to the n plus first power. And we saw examples on the previous page where that is definitely not true. Nevertheless, persistence is still a good, interesting property. And here is an example, a result that Dan Katz showed me some time ago, and I don't see it explicitly in the literature. He showed that if I to the n plus 1 colon I equals I to the n, then at least for that power, this anybody who's associated to I to the n is also associated to I to the n plus 1. And then Radcliffe proved with different methods, without using this result above, that if ideal is normal, so all the powers of I integrally closed, and if I contains the non-zero divisors, then persistence holds. Okay. So normality implies persistence. And then persistence holds for the following square-free monomial ideals. So Francisco Ha and Van Tuyl proved in 2010 that it's true for cover ideals of perfect graphs. And in fact, they conjectured that it would be true for all square-free monomial ideals. Then there were two papers, one by Martinez Mernal, More and Villarreal, and another one by More and Villarreal, all in 2012, that proved persistence for edge ideals. And Herzog, Rauf, Ladoyo in 2013 proved persistence for polymatroidal ideals. But I already showed an example in the previous page that there is an example of a square-free monomial ideal where persistence does not hold. And their examples derived from a graph defined by Gail Kalai, a family of graphs studied by Kalai. All right, so persistence, it appears for lots of examples, lots of families of ideals, but not always. And here, with Robert Walker, we studied ideals I plus J, where essentially you can think of it in the simplest case, we are starting in a polynomial ring C over a field F, and I has generators all depending only on one set of variables, and J has generators in a separate set of variables. So I plus J have no generators that have common variables. So then we want to study powers of I plus J. And one of the things we wanted to understand is if I and J are both have persistence, does I plus J have persistence? And we were not able to prove that. We do not know that result. However, if J, in this, what we do prove is that if J has persistence in the way that it's not sufficient that it just has persistence, but it has to be a non-zero normal ideal, then I plus J does satisfy persistence, whether I satisfies persistence or not. So persistence is like a persistence property, and it sucks in that extra I. So here I'm stating this persistence, the same result one more time. And I want to say a few things about our proof and our results. And the crucial ingredient in our result was the module decompositions of tensor products from the paper by Han, Win, and Go and Tran from 2017. And they studied symbolic powers of I plus J, and they proved some wonderful results about I plus J, and I'll come back to this paper recently. Anyway, we looked not just at the symbolic powers, but we constructed primary decompositions of powers of I plus J from primary decompositions of powers of I and of powers of J in the following sense. So here, this is the most technical slide that I have here. So we know that powers of I have only finitely many associated primes, so there's a list of them. And so for each power of I, we can write a primary decomposition, and not all of the primary components need to appear. So possibly some of those components that I list in the first blue line are just the whole ring. But some of them are possibly primary to P sub I. Now, from these primary decompositions, we now want to create a filtration. So for each prime ideal P sub I, we want the P sub ni's to form a descending chain. And so the way we form a descending chain is here with this. Can you see the highlighting?
Yes, we can see.
Okay, thank you. So with this intersection, now we force that the P primes, as we fix I, they form a descending chain. Okay, possibly they're again the whole ring, or possibly they're P sub I primary. And then just for completeness, we have P prime 0I as the whole ring. Okay, and then similarly, we define these filtrations of primary components for powers of J. And then, so now we want primary decompositions of I plus J to the n. It's really very natural. I plus J to the nth is a sum of powers of I times powers of J. So this, what is here is the relevant P sub I primary component of the kth power of I times the Q sub J primary component of the n minus kth power of J. And so this is this intersection works whether the
excuse me, there is a question. Is A same as R?
Oh yes, I'm sorry.
Yeah, okay. Yeah, thank you.
Right. Yes, thank you. So this intersection works whether the underlying field is algebraically closed or not. But if the field is algebraically closed, then these intersectants are primary, or they're the whole ring. Okay. And one thing that does hold, we know that the set of associated primes of all the powers of I plus j is just the sum of all the p sub i's plus q sub j's. Okay. Now, one thing that is true, so one thing for that, as far as persistence is concerned, if we have embedded primes of I squared and j squared, well, those embedded primes plus the minimal primes of j, of the other ideal, they appear as associated primes of the second power of I plus j. But if an embedded prime of a prime ideal of I, associated prime of I squared plus associated prime of j squared need not be associated to I plus j squared. They are associated to I plus j cubed, though, so that's the second result we have there. So we sort of have persistence, but we're not guaranteed that things fall in the right place. Okay, so and now, so persistence is sort of natural, but now we have opposite of persistence. With my undergraduate student, Sarah Weinstein, we proved that if we take any non-increasing sequence, so they can stay constant and eventually go down, of positive integers, then we can construct a monomial ideal such that the number of prime ideals associated to the nth power of that ideal equals the nth term in the sequence. So we are guaranteed that as soon as we have a non-increasing sequence, we can construct actually infinitely many corresponding monomial ideals I. Okay. So the construction pretty much goes as follows. So the sequence stabilizes eventually. So a non-increasing sequence of positive integers. So say that eventually the number is constant 8. So what we do is we construct an ideal that is very complicated, so let's call that special ideal, times a product of 7 variables. So those 7 variables will make sure that we'll always have at least 7 associated primes. But that 8th complicated ideal, we have to make sure that high enough powers of that complicated ideal have only 1 associated prime. But then the intermediate ones have more interesting results. And then in the intermediate ones, that's where the interesting induction happens in construction. Okay. But one thing we would like to know is, given an arbitrary sequence of positive integers, there exists an ideal in an Noetherian ring such that the numbers of associated primes agree with that sequence. Now, because of Brodmann's result, this sequence of positive integers has to be eventually constant. Okay. And we do not have an answer to this. I would still like to know an answer. But we do have partial results. So I want to talk about, so with Sarah, we have decreasing sequences. And here is a related result. So this is the same paper that I mentioned earlier that came up with my work with Robert Walker. This paper is by Ha Win and Nguyen Tran. Given an eventually constant sequence A sub n of non-negative integers, there exists a monomial ideal such that the depth of R mod I to the n equals A sub n. Okay, so A sub n equals 0 is true if and only if the maximal ideal is associated to I to the n. So there's some connection, definitely some connection with associated primes. However, we could have maximal ideal associated, and then intermediate prime ideals could be associated or not. So lots of interesting things are happening. Okay. So, and anyway, there is no such a general result for associated primes of powers of an ideal. Okay. Okay, so back to our question. We cannot restrict the R ideals to monomial ideals because as soon as you have a monomial ideal that is primary, then all of its powers are also primary. So we cannot strictly increase the sequence. The sequence A sub n cannot be 1, 2, 2, and still for us to have a monomial ideal. Well, if we cannot restrict our attention to monomial ideals, then life gets harder because monomial ideals, primary decompositions of non-monomial ideals tend to be quite a bit harder. So we need different tricks if we want to have increases in between. Obviously, I showed earlier some results, for example, that by Kaiser, Stehlik, and Shklerkovsky, where we start with the monomial ideal and numbers do increase. They can go quite a bit higher, but they cannot start with 1. Okay, so the other work I had with Jesse Kim, where we proved the big jumps. So the big jump is we started with prime ideals, and we want to study the number of associated primes of the squares or other powers of this prime ideal. And what we show is that the number of associated primes of powers is not bounded by any polynomial function in the dimension of the ring. So this was actually motivated by the work of Jason McCulloch and Irena Peeva, with their disproof of the Badgota conjecture. But I wanted to understand those results, but anyway, this is what we came up with. And here's a little bit of background. Grete Hermann, a student of Emmy Noether, published a paper in 1926, and then with some constructive results in Seidenberg 1974, Van den Vries and Schmidt in 1984. What they proved is that there exists a primitive recursive function that depends on n and d and doubly exponential in n, such that if you take any ideal I in a polynomial ring in n variables over a field with the generators of degree at most d, then that ideal has at most b sub n comma d associated primes. So we can guarantee up front this number of associated primes. The in these 3 papers show that this upper bound is doubly exponential. Okay, it could possibly be smaller, but they guarantee that it's doubly exponential. The construction that Jesse Kim and I have show that this number is at least singly exponential in the number of variables, but we don't know if there exists a doubly exponential ideal. I did some work some years ago on the Meyer-Meyer ideals, and there I showed that the number I showed concretely that the number of associated primes is at most doubly exponential, but I cannot prove that those doubly exponential potential associated primes are actually associated. So it's one of those recursive formulas that you get all the candidates for associated primes, but you don't know if they are all associated. So anyway, this question is still open whether doubly exponential is indeed needed. In another direction, Ananyan and Hoxter had a preprint in 2016, finally got published this year, that there exists a primitive recursive function that such that E, depending on M and D, such that any ideal in a polynomial ring over a field with at most M generators of degrees at most D, so here there's no dependence on the number of variables. So the number of associated primes is bounded above by this primitive recursive function. And again, what our work shows that we have some singly exponential bound on M. So it's still pretty big. And there has been some more recent work on these bounds by Caviglia and Yihue and so on. And anyway, so I already talked about splitting and spreading earlier on some examples. And so as far as I know, Jesse and I introduced the splitting and spreading. Splitting is a generalization what McCulloch and Pieva called step-by-step homogenization, but we don't need homogenization. We, in fact, we don't, we don't need that at all. Okay, so splitting is we start with an A algebra R with T is a variable, RT, where T is a variable over R, and then, R is an A algebra, and then the splitting would start from R adjoined T into R adjoined more variables, and we just, R goes to R identically, and T splits into, or it becomes a product of powers of these new variables. And in this talk, all C sub I are 1. The results for higher C's are a little more technical, but we proved some things for other C's as well. Okay, so this is a faithfully flat map. It commutes with intersections. Lots of good things happen. But what happens that if I is an ideal in, I should have said, if I is an ideal in R adjoint T, if I is an ideal in R adjoint T, and exactly S of its primary components contain a power of variable T, then the splitting of, I shouldn't have said of S. The splitting increases the number of components by n to the s minus s. So the heights don't change. The resulting ideal associated primes have the same height as what we started with, but the number of components increases. But this is still polynomial growth in the number of variables. So we started with some fixed s. No matter how we change n, this is polynomial growth. So splitting can help to some degree, but then we need a new method that would also spread the height. So spreading is more technical, and it adds more variables into the primary components and increases their heights. All right, so I don't want to give a the technical definition of spreading. I just want to say that instead of that nice map from RT to R adjoined Y1 through Yn, what we have now here is we do have a map like that, but we call it generalized graded. So grading on R adjoined T, and there's a grading on R adjoined the Ys, but they don't have to be compatible. Well, they have to be compatible in the sense that graded elements of R adjoined T have to map to graded components in the other ring, but we don't require the same grading. Okay. And then the splitting was result in the bigger ring, but the spreading is, we started with an ideal in the bigger ring, and we now want an ideal in the smaller base ring, and we take the ideal generated by the homogeneous elements in the base ring that map to the given ideal in the big ring. So it's somewhat technical, and I will show you examples later where different things can happen depending on your choice of grading. Nevertheless, there's still some good things that spreading satisfies. It's definitely not faithfully flat. There's not faithfully flat. There's not even a map there. It's just contractions. Okay, so I'll show you these examples how it works in practice. So first, we start with the ideal that I labeled B, and now one spreading here is we start with the ideal with the base ring now is field the joint x, y, z, z1 through z sub m minus 3, and we map into f, x, y, z, and all the z is mapped to, z sub I is mapped to z. So blue elements here are all in the kernel, and so if we make an appropriate grading, maybe actually here trivial grading works. This is exactly the spreading of P. The new ideal is the spreading. So we, the number of, this is still a prime ideal, but the height changed. And now we have, in this new ring, we have m variables, and we will split each of them into a product of v sub I new variables. Maybe all v sub i's are the same. And the result is a prime ideal of height m minus 1 in a polynomial ring in m times v variables over f. Higher powers of this prime ideal have 1 plus v to the m associated primes. So we increase the number of associated primes by a lot. So in particular, we can explicitly construct a prime ideal P of height 4 in 19 variables, such that all higher powers of P have exactly 500 embedded primes. So that's pretty big. Okay. And now the second construction, we started with the ideal that I labeled C earlier. And now this is definitely not a prime ideal, but we look at the presenting ideal P of the extended Riesz algebra of I. By the way, the same method that we use here also works for ordinary Riesz algebra or the I'm spacing out right now. The Riesz algebras, almost Riesz algebras. That's, what did they, Jason McCulloch and Irena Peeva called them, whatever they call. Sorry, I can't remember it now.
Small.
I think Riesz-like. Do they call Riesz-like?
Riesz-like, thank you. Yes, thank you. So the same construction works, but the extended Riesz algebra gives us somewhat sharper results. So we have to understand the presenting ideal of this. And then what we want to do is do some spreading, because spreading increases the heights. And when we increase the height, then when we do the splitting, the exponent on the number of associated primes increases. So we need to do the spreading. So the spreading of I that I'm looking at is this z1 through z sub n times x squared y squared. Now the map is the same as the one I talked about earlier here, but z minus z sub I is of course in all of the kernel. However, if we make the grading just right, so the multigraded grading, then z minus z sub I is not homogeneous, so I cannot throw it into the spreading of the ideal I. So the kernel, we do not put the kernel into the spreading of I. So this is somewhat unusual, and definitely it's different construction from the splitting. So this is down here, this is a possible splitting, spreading this whole of the original ideal. And what Jesse and I prove is that the spreading of the presenting ideal of an ideal I is the presenting ideal of the spreading of I. Okay, so if you ever need to understand the presenting ideal of something like this, for quite a few properties, it's sufficient to understand the presenting ideal of I with only 3 variables, and then take the spreading of that presenting ideal. So that's what we exploited in our work. Okay, and then once we have the spreading of this prime ideal P, we split the spreading, and the result is a prime ideal Q. So if there's some variable M that comes in, carefully chosen. The result is a prime ideal Q of height M plus 1/2, so M has to be odd, in M times V variables, and Q squared, so here we can only control Q squared. This has at least V to the M plus V to the M plus 7/2 embedded primes. So the upshot is here, there exists a prime ideal P of height 5 in 23 variables, such that P squared has at least 1,000 embedded primes. So this second construction doesn't give us as precise results as what we got in the first construction. And here in the second construction, we can only control the second power because we needed to understand P squared, the associated primes of P squared, more carefully in order to understand the associated primes of Q squared. Again, this spreading is not a faithfully flat map, so we don't have perfect control. And we thought this was increase to 1,000 embedded primes is pretty good. Okay. All right. So here with this work with Jesse is we looked at associated primes of powers of prime ideals. We showed that we can have very big gaps, but in all the ideals that we were able to, in this case, that we were able to analyze, the associated primes of P squared were the same as associated primes of higher powers. So we were not near the desired goal of, well, make a big jump and then be able to go up and down.
Irena?
Yes.
Can I ask a question?
Yes.
Do you have any understanding of the multiplicities of those primes you're constructing, of the quotients?
No, not at all. That would be a good thing to explore.
Thank you.
Other questions?
I don't see any questions right now.
Okay. All right. So in the last part, I want to go back to the question, or to the result from Ha, Win, Ngo, and Tran from 2007, where they proved that given an eventually constant sequence A sub n of non-negative integers, there exists a monomial ideal I such that the depth of R mod I to the n equals A sub n. And remember, I would like to have some results for set numbers of associated primes. But in my work with Rosie Risner, we looked at prior work by Banderi, Herzog, and Hebe from 2014, where they constructed monomial ideals, a monomial ideal such that its depth function has exactly M strict local maxima, and you can decide on that M ahead of time. And here is the construction of their ideals. You don't have to worry about the details so much, but the values of the depth function are 0, 1, 0, 1, 0, 1. So the 0, 1 is repeated M over 2 times, and after that it's constant 2. All right, so with Rosie, we looked at the numbers of associated primes of these. We thought that, well, since they have these jumps, maximum ideal associated or not, we would possibly have the same kinds of jumps on associated primes. But the story there is not so simple. So I will analyze this number of associated primes here. So The red part there is stable as soon as n is bigger than or equal to 2. So delta there is the Kronecker delta. So delta sub 1n is 1 if 1 is equal to n and 0 otherwise. So from when we jump from 1 to 2, the number of associated primes has a huge jump, and then the red part contributes constant after that. The blue part, if we fix m and vary n, that is stable as long as n minus 1 is less than or equal to m. And then after that, it starts decreasing to 0, and it becomes 0 when n is 2m plus 2. And then the orange part that's where we have that 0, 1, 0, 1, 0, 1. But as far as the number of, and then it stabilizes. Okay. And below, we computed some numbers explicitly for these associated primes. So again, in the first step, for going from 1 to 2, the number of associated primes has normally a big jump. And then what is not seen from the picture of numbers down here, that 0, 1, 0, 1, 0, 1 switch, you can see a little bit of it, that any rises, if they occur, are by 1, but then eventually the numbers decrease. And the eventual number for large n is, the number of associated primes is 1 plus 3 to the m. All right. So this, again, with the hopes that we would get some sequences of rises and jumps and rises and falls and rises and falls, being able to get first big jump, but then the only other jumps are at most 1, that was not all that satisfactory. So what Rosie and I did is we defined somewhat more general ideals, and they are more technical, but the m comma 2 are the original boundary Herzog-Hebe ideals. We can prove that the rises can be larger. They are not just 1 when they exist. The rises can be much larger, and then that 0, 1 cycle, that's not very visible in the numbers here. In these numbers, you don't see the 0, 1 jumps. You can see it in the brown 0, 1 jumps, but you don't see it in the numbers because they're so messed up with the blue and the red parts. But in the other BMR for other R, we can observe the cycles of period R longer, especially when n minus 1 is less than or equal to m. But then the construction, of course, is much messier, and we don't have complete numbers or the complete results. We have many numbers, but yeah, we don't. It's not complete yet. We have not been able to prove all the clear patterns that we have. Okay, I thought I would finish much later, so I did not prepare more slides, but I'm happy to take questions.
Yeah, thank you, Irena. We can take some questions from audience. They can unmute themselves and ask questions one by one.
So I have one for you.
Yes, yes.
Could you explicitly say what maybe the top 1 or 2 problems are that remain in terms of persistence or numbers of associated problems? What do you most want to solve at this point?
Okay, so the big problem is, so one problem is, given an arbitrary sequence a sub n's of positive integers, it eventually stabilizes. Does there exist an ideal I, obviously not necessarily monomial, such that the number of associated primes of I to the n is exactly the nth term of the sequence? That's one thing, that's more general. The second thing is, what are the restrictions for these sequences of numbers of associated primes for powers of for monomial ideals. Okay, so we know that monomial ideal cannot jump from one to higher, but what are some other restrictions on that? And then also, hello?
Yeah. Yes.
Oh, okay, maybe my screen went in. And then the other thing is if we have two ideals, I and j, in totally disjoint sets of variables in a polynomial ring over a field, and if both I is persistent and j is persistent, can we prove that I plus j is persistent? So see answers to these questions.
Thank you.
Yeah.
Very clear. Do you believe the last one?
I'll say yes. But Robert and I tried so many counterexamples. Actually, we asked you, we sent emails to many other people asking if they, for some examples, or if they knew something like this. And I think the general consensus is that there's no reason to believe that that is true. But all the calculations that we did, concrete ones, but there's only a limited number, it turned out to be true.
So there's a question, Irena, from Nina Gupta. Nina, can you ask your question?
Yeah. Hello, ma'am. Ma'am, my question is, these results are very interesting, but how does one compute associated primes? I have heard that it's very difficult to compute associated prime of a given ideal. Even knowing primary decomposition is a challenging problem. So
Yes.
how does you do it?
For monomial ideals, this is quite a bit easier. So for monomial ideals, as soon as you see a variable in one of the minimal generators that whose power does not not in the ideal, then you know that variable must be in some embedded primes. So just colon out that variable to as big of a power as it appears in the minimal generating set. And then you have a bigger ideal and you intersect with the ideal added that power of the variable. So now I have two strictly larger monomial ideals and you keep going. Okay. So for monomial ideals, you can do it. The problem with this construction, and this is a problem with the construction, not just for monomial ideals, but in general. So what you know is that the ideal I is I colon any element to a high power, giant power, intersected with I plus that giant power of that element. So you have strictly, if you choose your element well, then you have two strictly larger ideals. So where you colon out everybody that's associated to the coloned out part, that's also associated to the original ideal. But where you add the element, whatever is associated to this ideal plus the element need not be associated to the original ideal. So then there's extra process for eliminating. So, so how do you find associated primes in general? Well, the other way of doing it is you have to, you suspect that you have a family of associated primes, and you find what's called the witness. So a prime ideal P is associated to an ideal if and only if you can write P as I colon an element. So if you have a family of these elements, they're called witnesses. If you can produce witnesses and you can prove, oh yes, all of these prime ideals are associated, and then you can most likely also get the components for those primes. And then if you can prove that the intersection of those components is the ideal, then you know that you have the primary decomposition.
In general, means I suppose, is there any relation between the associated prime of I and I to the power n? Is one contained in another?
No, no. So
This is
the
maybe a very trivial question to ask.
no, it's not. It is not. Okay, 'cause I guess
Maybe
I
it's
have
true
to.
for prime ideals? No?
No, even for prime ideals. So this prime ideal in part B, that's a prime ideal, and the number of associated primes gets bigger, right? So for higher powers. And then the numbers can in general go down. That last example on the page, associated primes can go up and they can go down, right? So for computing the associated primes of non-monomial ideals, that gets harder. And that's why there are algorithms for doing it. There's a Yokoyama algorithm that uses characteristic sets. Then there are Grumner basis results. Then there are X results. So the Grumner basis results are Johnny, Traeger, and Zacharias, and the X results are Eisenbud, Huneke, and Vasconcelos.
Okay.
Thank you, ma'am.
Yeah.
Huge results.
Yeah. Any other questions?
This is Anant here. I have a question.
Yeah.
Irena. So this was about the comment you made about given a non-decreasing, eventually constant sequence like A1, A2, AN, and you said that there's a construction that you can do to get associated primes to be equal to that number for the nth power. And you made a comment there that you first do this, you construct an ideal where the constant part is 1, and then you add some variables to it. Is that
right? So say that this sequence eventually terminates in 8. Okay. So what we construct is an ideal that's a product of 7 variables times a complicated ideal. And that complicated ideal, the powers of that, high powers will have only 1 associated primes, very high powers. But in between, we have to construct that ideal so well that there will be, they won't immediately go down to 1. They will go down to 1 more slowly.
I see. So my question over here was, this is more of a curiosity thing. So you take this ideal that you have constructed, which eventually stabilizes to 1.
Yeah.
And then you add the variables like you did. How do the numbers change when you?
Anywhere you want to. Anywhere you want to. So maybe if we look at these examples C, right? So in example C, we can make a drop from an arbitrary number down to 1. But we do that drop immediately, right?
Okay.
And the reason we make that immediate drop is that x squared, y squared, z becomes redundant for the second power. But if we can make different powers of x's and y's there on the side so that the corresponding blue element becomes redundant after the 3rd power or after the 17th power.
And like if you place a restriction on the dimension, what kind of sequences will be?
Yes.
Will you be able to construct what will not be allowed? Is there?
Okay, I should. We are a dimension with the result with Sarah is polynomial in the. We have number of variables is polynomial in the number of how long the sequence keeps changing.
So this is part of your result.
Yes, yeah. Yeah, we have explicit construction.
Okay. Thanks.
Okay,
By the
Irena,
way,
1 or 2 questions if.
Yeah.
Okay, first is, can one predict when exactly the sequence of associated primes of powers of an ideal in polynomial ring will stabilize?
I am not aware of any results to that effect. So that 1974 paper by Seidenberg, that he did a lot of constructions. It's a very long paper, and controlling for the number of associated primes, controlling for the degrees of the generators, numbers of generators, for integral closures, for all sorts of things. That paper may have the stabilization, but I don't think so. I'm not sure. I don't think it studies stabilization there.
Mm-hmm. Yeah. And what about in characteristic P? Suppose you take excellent reduced ring and look at the tight closure of powers of an ideal. We know that it will stabilize at some point. But do you expect a better behavior there?
You mean that the number of associated primes of the tight closure
Of
of
powers?
powers stabilizes? Oh, I see, for your good rings. So in this, what I presented today, we didn't even look at integral closures, which integral closures are maybe the next step, because there's the associated Riesz algebra, Riesz ring, whereas for tight closures of Frobenius powers. Oh, you're talking about tight closures of Frobenius powers, or
No, powers of an ideal.
powers. I see. I did not look at that at all.
So the Riesz algebra is still finitely generated if the ring is
Right.
analytically ramified.
Yeah.
But my general question is, given a good filtration, that is, if the Riesz ring is Noetherian, how to really predict when the associated primes will stabilize in terms of numerical invariants like multiplicity or analytic spread or something like that?
That's a good question. And this last result on this page may be of interest for taking integral closures or tight closures of powers as well.
Mm-hmm. Yeah. And the only numerical result which I know is due to McAdam, which predicts when a prime ideal is associated to integral closure of I to the n for large n in terms of the spread of the localization. And but if you take some other filtrations, I know of no such numerical characterization.
Right. Yeah.
And the stable set should have some numerical characterization. If your ideal is nice.
Right. Yeah. Well, so McAdam's book on these asymptotic primes associated to high powers and integral closures of high powers, there are a lot of results in there, but I don't remember anything about when it happens numerically.
Yeah. Okay, any other questions?
Jensen here.
Yes.
I have a question regarding primary decomposition of binomial ideals. Do you have, is there, monomial is reasonably, easy to handle. Reasonably in the sense, I understand that it's not easy, but when it comes to binomial, it loses kind of, all structures when you take powers. Is there a pointer in that direction?
Right, that powers. So there are results. There was a paper by Eisenbart and Sturmfels on decompositions of binomial ideals.
Yeah.
All components are binomial. the underlying field is algebraically
Yeah.
closed. But you're right, when you take powers,
Powers.
then you lose that information.
Yeah. Yeah, okay. Okay, thank you.
Let's see. Okay, so I don't see any further questions. So let us thank Irena for her very inspiring talk. And we thank her for getting up early in the morning and waiting for us. And thank you very much. We have a lecture on Friday by Tony on homological algebra on complete intersections.